Okay guys, good evening. This is Wei. So here I'm just recording a tutorial video for the lab 1 because I will be away for next week. So I won't be here for Monday and Tuesday for the Q&A session, but I will still ask one of my friends to go there and help you guys if you have any question. But I'm also recording this video so that you should be able to find all the essential information you need in this video. So hopefully it's helpful. Okay. Again, my apologies for the inconvenience. Okay, so let's talk about lab 1. I'll try to be efficient and cover the main points we did in class today, this week. Okay, so this one is about t-test and the background story is that we're investigating the relationship between speed limits and traffic fatalities. So basically, at 1995, the US government said each state has the chance to increase the speed limit, and out of the 50 states and DC, 32 of them decided to increase the speed limit, which means 19 of them retained the limit. So we basically have two groups here. One is, I call it yes group, means the states which increase the speed limit, and no states which retain the speed limits. And here the response we gather, is the traffic fatalities in 1996 and 1999. And here we are more interested in the percentage change because the absolute value of FAT96 and FAT95 and FAT96 depends on the population of the state as well as the size and a lot of other factors. So it's more meaningful to look at the percentage change. So here this value, percentage change, measures the change of traffic fatalities from 95 to 96 for each state. So if this value is positive, it means the traffic fatalities increased. If it's negative, it decreased. If it's around zero, so nothing changed, okay? So if we take a look at the data, we have 50 states and DC. We have the indicator variable. We have FAT95, FAT96, and we have the percentage change, okay? Okay, so first the question asks you whether this is an observational study or experimental design. So obviously this is an observational study because here we have no control on the variable increase. So basically, for example, for Alaska, whether Alaska increases speed limit depending on the legislature of Alaska and the choice of the people in Alaska. And as the experimenter, we have no choice in manipulating this variable. So basically, we observed all this information, so it's a pure observational study. And for observational study, we say that we can only make correlation or association interpretation. So basically, we say at the end of the day, we can say maybe there's a connection or a correlation between speed limits and traffic fatalities, but you can say that the increase, for example, the increase of traffic fatalities is caused by speed limit. So here it asks you whether you can make a causal link. No, because it's an observational study, okay? There are so many other confounders, that confounding variables we cannot measure. And the next part is about generalization. Okay, so generalization depending on the population of interest. So for example, if the population here we define it's the U.S. The United States, then we can, because the sample we have is actually the population, so it's a very special case. But if you say that if the population you define is the whole planet, the whole Earth, right, all the people, then you can't, because all the things happening in the US might be different than other countries, so it might not be very transferable. So this really depends on what's your population, okay? Because US is not a simple random sample. I mean, if we look at that case, so it's a kind of a unique setting in this case. Okay, for question 2. For question 2, we're going to do three things: the descriptive stat, the box plot, and the percentage change, okay? Before we do that, for the variable increase, because it's a categorical variable, let's change the sky into, from scale into, let's say, ordinal, okay? And then let's do the export thing. So we do analyze and then descriptive and then explore, okay, and we are investigating the percentage change factored by increase, okay. For the plots, we don't need streamlit, but we do need the normality plot, okay, and then continue, and then okay. So let's take a look at the output. So first, okay, it's coming up, okay. So this is the descriptive table. This is the QQ plot, okay, and then we have the box plot here. So let's take a look at the question. So for 2A, it asks you for the descriptive, and then it asks you to compare the means and standard deviation. So when they ask you to comparison, it's very easy. Say which one is bigger. So simple as that, don't overthink, okay? So for example, for this guy, for the no group, I have a -8, which means for the states who didn't increase the speed limit, the traffic fatality is actually decreasing by about 9% in average in my data. Again, I injected a noise in my data, so the number will be looking different than yours. And then we have the yes group. The yes group has a positive 13% of increase. So my no group has a smaller mean, and for standard deviation, this is 31. This is 21. So this one is bigger. Okay. So 2B asks for the confidence interval and it asks you some interpretation. So the CI is given here. So the CI here, as you can see, is part of it is positive, part of it is negative, which means that there might be a chance that the mean of the percentage change of traffic fatalities in the no states might be 0. But for the yes group, we see there is the entire CI is positive, which means that it's going to increase. It also asks you which one is wider. So here the no group is wider. Okay. This is because if you look at the formula for confidence interval, the length of the confidence interval equals to 2 times margin of error, and margin of error equals to the critical value times the standard error. So here you see that the standard error for the no group is bigger than the yes group, so that's why the CI is wider. Why the SE is bigger? This is because there are more variation in this group. Okay. There's a little bit overlap. You will see that between these two intervals. So a little bit overlap means that there's a small chance these two means might be equal. Okay, so that's B and C. For E and F, so for E, for box plot, so for box plot, we take a look here. So here when they ask you to compare this, the center and spread, so center here we have medium, so the yes group have a larger medium. For spread we have IQR, and the IQ looks quite similar for this two group. For the shape, this one's a little bit left skewed because, because of this outlier. This one is quite symmetric, and we have one outlier here, this the third data point, which is the DC. And for box plot, for the QQ plot, for QQ plot is used to test normality. So here, the solid line is reference line and the points are your data. If your data are close with the reference line, then it's normal. So here we see that the majority seems to quite normal. We do have an outlier here, but you might say that it's a little bit of violation. For the yes group, it looks pretty good because even though there are deviations, but the deviations are quite random, so it's looking pretty good. And for D, it asks you to do an individual one sample t-test for each group. So first we have to do select cases. So if we do data and then select cases, and then we do if condition, so if what? If increase equals to normal, then equals to 0, then we are selecting the no states. So no states, okay, if you check your data, you will see that all the yes states are crossed out. So okay, yeah, like that. Okay, now let's do one sample t. So analyze compare means one sample t, and then we select percentage change. We're testing against 0, and then we do okay. So the t-value here is the p-value here. So the sigma here is the p-value. The two-sided p-value is larger than 5%. Okay, so in class the teacher might have asked you to do like using, for example, if it's smaller than 5%, then you see it's strong evidence and then mild evidence. That's okay as well, but it's okay if you can compare this to 5%. I'm okay with that too. So here we're not rejecting basically because the data kind of supports null hypothesis. So this is for the no group. We have large p-value. And let's do the same thing for the yes group. So we do data and then select cases. Instead of increase equal to 0, we're going to put this as 1. So we're choosing the yes states, and then we do OK, and then we do the same thing again. So analyze compare means one sample t-test, and then we do the same thing, and we will see that the p-value is very small. Basically means that there's strong evidence saying that the yes group the percentage of change of yes group is non-zero, which we did see in the summary statistics because the mean is 13%. So there's a positive change. Okay, that's basically everything for question 2. Okay, let's go with question 3. So question 3, we're doing some t-tests to compare things. So first, 3A is asking you to compare, to ask you to conduct a test to show that whether the average percentage change was greater for the yes states versus the no states. So here we're doing hypothesis testing. So here if we're using P0, P1 to represent the states that increased the speed limit and P0 as the ones who did not. Okay, this is question 1D. That's your hypothesis for 1D. For question 2, here we'll have to decide which test to do. Because we're doing means and we have 2 samples, and because the yes state and no state are independent samples, so we're doing an independent sample t-test, and this is a null hypothesis. So the null hypothesis is saying that these 2 percentage change is the same for these 2 groups, and then alternative says that the yes group the yes state is greater. So the keyword here is greater. That's why we picked a one-sided test. Okay, now let's do the test. So before we do the test, we have to switch back, so go back to all cases, okay, and then we do okay, and then we do analyze and then compare means to sample independent sample t, and then we put percentage change, the grouping variable is increase, and then we put the first group as 0, so the no states, second group as 1, the yes states, and then we do continue, we do okay. So this is the table we need. So first let's take a look at Levene's test. So Levene's test is asking for equivariance. So here the variance, the sigma is large. Basically we're not rejecting. Not rejecting meaning that we kind of go with the null hypothesis. The null hypothesis says that equivariance. So we're going to go with equivariance, the first row. Similarly, you can look at the standard deviation, the ratio, it's smaller than 2. So we'll go with equivariance. So for equivariance, we see that the p-value is very small. So the two-sided p-value is 0.003. So we have to divide this p-value by 2 because we're doing a one-sided test. So, and compared this with 0.05, we're rejecting. Rejecting meaning that there are significant differences between the yes states and no states, okay? So here all the questions, here they ask what's the distribution of the test statistics. So here we're doing a t-test, so it's a t distribution with 49 degree freedom. Okay, 3B. 3B, it asks you to comment on the assumption of equivariability. Again, equivariability is not an assumption, so the question here is a bit wrong. We're saying that we can do the test under either equivariance or not equivariance. So here is a choice, it's not really an assumption. The confidence interval here. So the confidence interval here is from this guy to this guy, see, minus 39, 37 to minus 7. So the whole interval is negative, which means the 0 group is always smaller than the 1 group, which kind of fits our analysis here. We say that the yes states has a larger percentage change than the no states. Okay, that's 3. For 4, it's basically asking you to recreating the test statistics here using the formula in your formula sheet. Okay, so basically this is kind of like a homework question. I'm giving you the sample size, sample standard deviation, sample mean. All of these can be found in this table, okay? And then using these numbers, you have to figure out how to do a 2-sample independent t-test. And so yeah, so hopefully your hand calculation match this number. So you can either do typing all the equations, or you can do write by hand and take a picture. Okay, that's the first part of the homework. And the second part, we're investigating a different variable. We're looking at not the change, but actually the traffic fatalities per 1,000 people in 1996. So we're using this new variable, FAT-PCPTA96. And then we're going to do the same thing first. We're going to do the explore thing. So basically the descriptive table, the box plot, and the normality plot. Okay, same thing. Let's do the explore again. So analyze and then descriptive and then explore, and then instead of using percentage change, we're going to do PCPTA96. We do OK. So let's take a look. So the descriptive table, we see that for the yes group, the mean is almost the double of the no group. For the box plot, we see that For the center, which is the medium here, the yes group is higher. The IQR is also larger for the yes group. Both of them are right skewed, and there are two outliers here. Okay, so and for the normality plot, we see that there is a little bit of deviation here. Okay, it's not very big, but it's a little bit violation there. But this one is a little bit stronger because we see a pattern here, so it's going up and going down, which shows a little bit of skewness. That's why for question 6, it asks you to do a transformation, because now we see there's a little bit of non-normality in the data. We're going to fix this by doing a log transformation. So for question 6, we're going to compute a new variable. Basically, we do transform compute variable, and then we name the first variable. Sorry, this is when I was injecting the noise. You should not do this, okay? So we're going to name the new variable log underline pcfat pcpta96, which is a natural log, which is underneath arithmetic, and then we have the ln, and then put this one here, and then we do OK. So okay, so if you check your data, you have a new column, and I'm going to study this new column. Okay, so first we're going to do the box plot and normality plot, and then we're going to do the t-test on the new variable. So first, let's do the explore thing. So analyze descriptive, and then explore, and then instead of using this guy, I'm going to use this guy. Okay, then we do OK. So for the box plot, this guy actually, this one is really normal, really symmetric, but this one is actually a little bit of left skew, but it's not too bad. If you take a look at the normality plot for my no group, it's still a little bit of problem. It's not perfect, but for my yes group, the improvement is significant. We can see definitely a big change for the yes group. Okay, now let's do a hypothesis testing on the new variable. Okay. Okay, so let's do analyze, compare means, independent of t, and then we use the log PCPTA. Okay, then we do OK. So based on the Levene's test, the p-value is large, so we're going to go with equivariance. You can also see the same thing from standard deviation. The ratio is smaller than 2. So equivariance, we see the p-value is very small. So again, we're doing a one-sided test. Why? Because the keyword here is greater. Okay, so for one-sided test, my p-value is smaller than 5%, so I'm going to reject it, saying that there is significant difference between the no group and the yes group, and specifically we mean that this sentence is true. Okay. Here it asks you to interpret the results in the original scale, but actually for the test statistics and p-value, it won't change with log transformation. So here I think this part is a little bit weird. I mean, here we are saying that the log differences, log PCPTA 0 group equals to 1 group. And you can do exponential transformation here. Basically means that the no group and yes group are the same. So now they're different. Okay, that part is confusing. But what I'm saying is the test statistics and p-value doesn't change with the log transformation. But for this part, it asks you to do the interval part. We do see difference because here it asks you to interpret the estimated difference. So the estimated difference and interval. So the difference is here. So the difference is basically this number, okay? And this is the interval. So how do we interpret it back? So basically it goes like this. For example, in my case, interval is roughly minus 0.066. So this is the log scale difference. In order to get rid of the log, I take exponential. So here log a minus log b equals like log a over b, and I do e power, so this one is gone. I basically have a ratio. So mu1 over mu1, mu0 over mu1 equals exponential this value and equals this much. And interpretation here goes like this. So we're saying the ratio. So basically the mu0 is about half of mu1 in average, okay? And then you do the same thing for the confidence interval. So basically you do the exponential thing for the lower bound and for the upper bound, and you get a ratio, the confidence interval for the ratio, okay? And that's pretty much everything. It's quite simple, right? Okay. Okay, yeah. Bye.